Okay, this next section will be a bit heavy on some basics of MR physics because I think it's important for you to understand how the images and the signals are generated and how that gives rise to the artifacts that you have to be aware of and then correct. So the focus will be for you to actually have a brief understanding of how the MR signals are generated, but more importantly, where do those artifacts come from that give us so much of problems? Because artifacts, yes, they are false signals, erroneous signals, wrong things that show up, because not everything that you just image from a machine is actually real, sad to say. And the focus actually in this lecture to talk more about the portion called the preprocessing, and then the next 2 days, Professor Bonito and Professor Zareski will teach you heavily on the network processing. Okay, so if everyone's here, I think I can begin. So the goal for this next hour and a half is to understand the source of MRI contrast. You remember the intensity values in the three-dimensional matrix that I told you about? Where does it come from? How is it generated? What does it mean? And in the process of doing that, we are moving towards the main goal, which is to understand how do imaging errors in your data which you actually need to take care of, how do they arise and perhaps how do you correct them? So we start with a view of this fabulous machine, the magnetic resonance imager. If you haven't seen one, it's this big thing right here. You just lie on the bed and your head or your body goes into something like this called a coil. Okay? And the important parts really for you to know, there are three main components. One is called the B0 or main magnet. Okay? And that's this huge circular thing here. And it takes a lot of power, it takes a lot of cooling. It's really expensive to maintain this huge magnet, right? And when you turn it on, you can't turn it off, because if you turn it off too quickly, you damage the magnet, you quench it, you have to refill with tens of liters of helium, which is expensive, all that bad stuff. And when you hear news about 1.5 Tesla, 3 Tesla, 4 Tesla, 7 Tesla, that refers to the magnetic field here. And for your point of reference, the magnetic field of Earth's gravity is 5 to 6 orders of magnitude smaller than 1 Tesla. Right? That's 100,000 to 1,000,000 times smaller than 1 Tesla. That's the Earth's magnetic field that gives you gravity. You go close to this, I think it's been said, if you actually have a metal chair or something, it sticks to the magnet. You have no way of pulling it out, and the only way you get it out is you have to shut out the whole magnet. And it's an electromagnet. So this is the main B0 field, and we'll discuss what it does. The second set of fields are what you call the gradient coils. There are 3 gradient coils, and they are aligned on the inner side of the B0. And they are called gradient coils because they set up a magnetic gradient. And later on in this lecture, you will see why do we need a magnetic gradient. And these are the ones that actually get switched, they get changed, they get modulated with time to generate your sequence. The B0 is just like a flat, steady field. Nothing happens to it, it just stays there and it just keeps going on. The third important component is called the RF coil, or sometimes you refer to this as the B1 field. Okay? And this RF coil is basically, it looks like a cage. If it's a cage, it's probably a cage coil. Sometimes you ever hear about surface coils. It has a specific function that is to transmit an RF signal and to receive. This is actually your receiver of your MRI. This is where the signal comes from. This is what detects the intensity values that are being returned. Changing this in concert with this, changing the magnetic parameters, which are electrically generated, gives you the pulse sequence. And this is done within the B0 here. Okay, so 3 important components: the B0, the main magnet, B0 main magnet, same. The B1 or the RF coil, same thing. the gradient coils, and there are three for X, Y, and Z direction. Okay. And this is some pictures of what it looks like. Just roughly, you can see that in between these coils is filled with helium or liquid helium, and that's to actually get a superconducting magnet, to get a high enough large magnetic field. This is just so you understand how this works. Now let's go. Okay, this is the most challenging part, because I'm going to try to summarize in 10 minutes what people take a whole course or whole program to teach. Right, this is the principle of MR neuroimaging. Now, all of us have water in our body, and water has an abundance of hydrogen atoms in them. Okay? And these molecules have a property called a spin. Okay? You can think about that as a kind of magnetization. And each of them, any one time, like I take my arm right here, right? There's water molecules all in here. And every molecule has a spin direction. And the spins, when you talk about spin, there's a local magnetic field. And if you remember, a magnetic field has a strength and a direction, right? I mean, all of us have taken a magnet, and you know that it actually pulls a metal thing in a particular direction, right? So a magnetic field has both a strength and a direction. That's called a vector. Right? A vector has a strength and direction. So every molecule in your body has a very weak every hydrogen molecule in your body has a very weak magnetic field, and in a normal person like me and you, it's oriented, the direction of magnetic field is everywhere, it's pointing everywhere. Now what happens when you put all of this collection of hydrogen atoms in the water in a B0 field, which is very powerful? Well, guess what? All the magnetic fields of the individual water molecules align in the same direction. So I think you've seen this before with your metal sprinkles. You put a magnet underneath, all the magnet sprinkles sort of go into a line, right? So that's what happens when you put your human body in a B0 field. All the water molecules in your human body all get aligned in one direction. Okay? Right, this is the tricky part. Well, when I say in one direction, that's the Z direction. The magnetic field can be pointing up, or it can be pointing down. Or in the case of an MR scanner, okay, in the case of the scanner, the magnetic field is in the Z direction. That's actually going through the hole. Okay, so if I'm sitting, lying down in this MR machine, in the board, all my water molecules, the hydrogens, are aligned either in this direction or in that direction. If I have one atom aligned this direction, one atom aligned this direction, there is no net magnetic field, because they cancel each other out. Okay. I'm not going to have all of them aligned in this, all aligned in that. There's going to be a small difference, a small number of magnetic fields that tend to be aligned in one direction, excess, right? So I told you that if they align in one direction, they actually can point in two directions, right? A line on one axis can point in two directions. They're not equally split, which means that you have some net magnetic field in one direction. Okay, so is that point clear? So do you understand now that when you go sit inside a B0 field, all your water molecules are aligned along one axis, but there is a net field strength pointing in one direction, and there is the small excess number of water molecules that have not cancelled each other out. Okay, so that's what happens when you sit in the B0 field. But that's not what happens when imaging happens yet. Okay. Now, perpendicular to the B0 field, I have two coils, two electrical coils. They are like your inductors. They're literally inductors. Okay. And what happens is you pulse a microwave pulse on it. And that's basically an a surge of electricity, for want of a better word, trying to really dumb down the language, okay, layman. You pulse a wave at a particular frequency, and I think all of you probably have done physics in high school, and you remember Faraday's law, when you actually have when you actually move a wire in a magnetic field, it generates current, right? And when you actually pass current in a wire, in a magnetic field, you can actually induce current elsewhere, right? So that same principle is what's happening here. When I pulse an oscillatory current through these two coils, I'm generating a magnetic field around the coils, perpendicular to the B0 field, and that's going to shift the direction of the net magnetization perpendicularly. Okay. Now, these coils, there are two of them, and they are located 90 degrees. We call this quadrature. So there are two coils, they're located 90 degrees, physically 90 degrees angle. We pulse an RF signal, and that's called the B1 field. And when you pulse that RF signal, you are generating a magnetic field which influences that differential water molecules to have their direction tilted perpendicular. So this is what's happening. So the reason this is oscillating is because I am pulsing an oscillating wave on these RF coils. So it's actually spinning the direction of the magnetic field to be perpendicular. So it starts out from the B0, it starts out pointing in the Z direction along the ball, like here, upwards. And then I pulse this with a continuous wave like this, a short wave like this, oscillatory wave. And that forces the direction of the magnetic field to just kind of spin downwards, and it's actually pointing perpendicularly. Okay? Right. So thus far, I've explained to you what happens to your water molecules when you go sit inside a B0 magnet. And then we've done our first intervention is we've just pulsed a current through these two coils to tilt the magnetic field of your magnetic direction of your water molecules in your body. Okay. After you do this, if you just leave your body like that, what happens is, over time, the direction of the magnetic field is going to decay and go back to the direction of the B0, the main big field, right? Because you give it the initial magnetic field, it has moved the direction, then the magnetic field has disappeared. And then your water molecules will gradually reorient their magnetic field direction towards the direction of the main B0 field. That time decay is your T1 contrast. Okay, so when you see the anatomical images that I showed you earlier, you have some very white areas and some very dark areas. The white areas are the areas of the tissue, okay, where the number is large. I think the T1 it actually decays very slow. So the reason we can generate anatomical images of the brain is because different tissues, different clusters of cells in your brain, the magnetic fields of the water in those cells decay back into the B0 direction at different rates. Okay? So the ones that decay with a very fast rate, they appear black. The ones that decay with a slow rate, they appear white. And that gives you the contrast. So that's an anatomical contrast, that's called T1 contrast. Okay? And this is actually illustrated here, because as you can see from this, it's illustrated here, as you can see from this pink direction. So we are continuing from here. We did the pulse first, and the pulse brings the direction of magnetization perpendicular to the B0, and then you stop the pulse. Okay? You stop the pulse, the direction of the field will oscillate, and it will return back to the direction of B0 this way. And as it returns, this is the signal that is being detected by these two coils, the RF coils, the B1 coils. Okay? So the B1 coils have two functions. First, they excite the water molecules in your tissue to make it change direction. And after the direction of the magnetization has changed, it records the decay of that magnetization, again, still using Faraday's law of induction. Okay? So, is this okay? So what's happening here is, what you see here is, this is the magnitude of the magnetization in the Z direction along the B0 axis, the main magnet axis. Over time, as it decays, the magnitude of course increases, but in the perpendicular axis, where you're actually measuring, there is a decay, an oscillatory decay like this. And this is called the free induction decay signal. Okay? And what we measure is the parameter of this decay. That is the T1. Now, there is another mode of contrast, which is the T2 contrast, or the T2 star. Once you tip the magnetic field to perpendicular to the axis, and you leave it over time, it's starting to decay T1 to the T1, but there's another decay that's happening, and that decay is happening in the direction perpendicular to the B0 field. What's happening there? All your hydrogen atoms are interacting locally with each other, as well as with the magnetic content in your brain, your blood cells, your any kind of iron containing things. And what's happening is they lose their coherence. They're not all pointing in the same direction anymore. They start to point in different directions along the perpendicular plane. And when they start to point in different directions, their strength, their magnitude starts to cancel each other out. So you see over here a decrease in the amplitude of the magnetic field along the perpendicular plane. And that is called the T2 star contrast. And these are the two sources of contrast that we detect in MR imaging. Everything else is derived from this. Okay? So this contrast is actually decaying also exponentially, and the value of the T2 parameter is actually the rate of this decay. This is actually an exponential decay for those mathematically inclined, so it's actually the e to the minus at is actually the alpha parameter there. Right? That's what we measure. Okay. So this is T1 and T2 decay. So when you pulse with your B1 coil, this thing is tilting towards a perpendicular direction. After you remove the pulse, T1 and T2 decay happens simultaneously. But the T1 decay is much slower than the T2 decay. And so you actually see the magnitude reduced in T2 first, and then it will get restored in the B0 axis through the T1 decay. Okay? Right. So the key point is that brain tissue will have different rates of decay, either in the T1 or T2 way, and we play around with pulses to give different physical interpretation of the T1 and T2 decay. So at this point, it's still a little bit fuzzy because we're going to go into actual physical sequences, anatomical sequences, but for now, it's enough for you to understand. You have an RF pulse perpendicular to the B0, which tilts the magnetic field direction, and at which point two natural processes come into play, and that decay time, the T1 and T2 decay, is what's being measured. That's what you need to understand at this point. Okay, so anatomical MRIs we saw, the MRI of your brain, the three-dimensional matrix, that is a T1 weighted contrast. Diffusion weighted and resting state fMRI, or just fMRI, task-based fMRI, they use T2 contrast. Now, I'm going to complicate things a little bit more. As I told you, there's going to be this T1 decay, and then the T2 decay, the magnitude decreases in time. You don't actually start measuring the MR signal when you tilt, because this starts to decay. You can actually play a little trick on the situation. You can actually force this T2 magnitude, the strength of the T2, to actually reduce to zero, and then it kind of grows back. And that's called echo generation. So echo generation is a very important part in MR imaging, because you need to artificially induce a defacing in T2 so that it can actually reface and you can actually measure it at that point. Okay, what do I mean by that? Okay, now take a look at this one here. Okay, I'll explain it to you. Okay. Let's wait for the animation to use. Okay, we start when it's pointing outwards. So this is when the tip happens, and then this is the T2 defacing. Then you introduce a signal to actually flip the angles, and then you see it converging together. Because the T2 loss of coherence is happening in the same direction. So if you somehow were able to change the orientation of the magnetic field, as you saw that flip, you can actually force all these dephasing signals to rephase, and that gives you a signal that then comes up in strength, and this is actually measured. So let me try to recap the main point. This axis is time. Okay, at this point, all your hydrogen atoms are facing in the B0 axis. When you start at this point, you apply the B1 field through the coils to make the magnitude perpendicular. And then it starts to decay in T2 and T1, but the T1 decay is actually kind of small. This is the T1 decay. This black line actually isn't real. The blue line is real. So the T2 is decaying here, it's dephasing. And then you artificially have a sequence that flips the direction of the H molecules, so that as they're dephasing, suddenly you trick them, they are sort of rephasing again. Okay, if you're not quite sure what physical mechanism is, don't worry. The key point here is we can induce some kind of orientation changing, again with a pulse that causes the signals to strengthen again, and that strengthening here is called an echo. Okay, and that's when you detect the signal. Okay. Right. We are almost through the tough part. Okay. So this is what happens when you are taking a measurement from one voxel in your whole body. Okay. So you can, as you can see, the measurement has associated with it a decay time as well as a frequency. A frequency meaning there is a specific rate of oscillation, as well as decay. Decay means you see the strength of the magnetic field actually goes down. So there are two parameters that are measured in your signal, right? But this signal comes from one voxel. So the signal has with it a frequency associated with it, and it's coming from one voxel, one intensity value. So how do we get from all the voxels in the brain? Here is where we play a little trick. We force each spatial location in the brain to give out a signal at a slightly different frequency. And that's how we extract individual intensity values. So what we do is we first prepare the brain in some way so that when you excite with the tipping, different parts of your brain are going to decay. They're going to be decaying at different rates because that depends on the local tissue property. But each region of tissue is going to be decaying with a different frequency, slightly different frequency. And the way we do that is we have a magnetic field gradient throughout your head. Okay? Because there's a property of the spins that the rate at which they oscillate is proportional to the magnetic strength, the field strength, the amplitude, the strength of the magnetization that they experience locally. So this is where the gradient coils come in. The gradient coils allow you to give each local tissue section a slightly, marginally, we're talking about parts per million, different magnetic field, so that they will decay at a slightly different frequency, and we are able to disentangle these different signals because they are at a different frequency. The engineers among us will know you're using the Fourier transform for this, right? But conceptually, that's the process. So this is what it sort of looks like. Okay. Let's say this is your body. Okay. This is your head. And your head has three regions. Square head with a very bright region, a very gray region, and a dark region. And here you actually see the rotation of the magnetic fields in the perpendicular plane. The B0 field is coming out of the page. So this is the perpendicular plane. So if I don't do anything, if I'm not playing around with giving a different magnetic field on the head, you see all of the magnetic fields are actually rotating at the same frequency. But now, if I apply an X gradient, meaning I'm changing the magnetic field slightly linearly here, you will observe that at the higher value, this spins faster, this spins slower, this spins slower. So I can, and while they are spinning, they are also getting shorter. So the rate at which they get shorter is the decay time, that's your intensity value. The speed at which they spin allows you to say, I have one intensity value for this row, one intensity value for, this column, one intensity value for this column, one intensity value for this column. So this is how the spatial encoding is done in MRI. So if the gradient was in the Y direction instead, okay, this column is going to precess at the same frequency. This is going to be faster than this, it's going to be faster than this. Okay. So in summary, to generate this signal of MRI, I need to excite the H molecules to a direction perpendicular to the magnet ball, and then I need to measure the rate at which they decay. But because I want to make multiple measurements simultaneously from different spatial regimes in the brain, I need to induce a magnetic gradient. I need to slightly change the local magnetic field at each point in the brain, and I use the gradient coils to do that. Okay? And this gives rise to something called a pulse sequence, because it is a sequence of electrical pulses that give rise to these magnetic properties. What this is. So this RF pulse, this 90 degrees, is the energy that you're injecting into those two RF coils to tip the magnetic field 90 degrees perpendicular. But as you're doing that, the Z gradient field is also on, so that you only select a certain region in the Z-axis, some axial plane. So I'm just going to select maybe one plane here or one plane here. That is what this magnitude does. Secondly, I can also encode the frequency, which is also setting this magnetic field here in the X direction, and I'm encoding, and when I set the gradient field here, what's happening is there is a slightly different magnetic field experience along the X direction that allows me to encode. So I'm actually skipping the other part, which is you need both frequency and phase to encode in 2 dimensions, and you can use the pulse selection to encode in the Z. Okay. I said this takes a whole semester to just teach, trying to cram it into 10 minutes so you get a flavor. The key points are we are using the gradient fields to give you differential frequencies and offset. So offset is phase. So if the wave looks the same but it's offset, that is the phase. And that gives you the position, allows you to extract the intensity value for different position, because you get a summation of all these waves with a different, slightly different frequency, and each wave has its own decay, and that decay is what we are measuring. Okay?
Question.
Yes?
Which gradient refers to what? Like slice selection refers to, I think,
Okay.
Z.
Slice selection typically refers to Z. Frequency is typically done on X. Phase is done on Y. We don't quite put it here because they can change it. Pulse sequences can change it and all that. But traditionally, conventionally, just talking about normal stuff, slice selection always in Z. That is the superior inferior direction. Yeah. But as I said, that can change. You actually have enough flexibility in the MR to change directions and all that. So the important points are, I have a sequence of pulses that I turn on and off the gradient magnets, as well as a wave oscillatory pulse through the RF that in the end gives me a signal, and this signal is from, if you don't have the gradient pulses, it's from one whole region. If you have the gradient pulses, all the signals from each individual region is sum, and that's what you detect here. Wait, sorry, it's not all sum. Typically, you select maybe one row or something like this. It's not all sum. Yeah, it's not all sum. You actually have to repeat this many times. I think each echo is it's one voxel, I think. Yeah. So you actually have to have a series of these going on and on and on and on, and then you get all the numbers out and you assemble the image. Okay, why is this important? Understanding this gives rise to all the distortions which we will try to correct. The important parameters to note is from the start of the excitation pulse, the tipping to 90 degrees, to the actual signal, the echo, that's called the echo time, typically abbreviated TE. Okay. Yeah. And you have to repeat this sequence by the total number of voxels that you want. So remember the anatomical sequence we talked about, 512 by 512 times 36. So you have to repeat this whole sequence, 512 times 512 times 36 times. And this typically happens on the order of, I think this is a few hundred milliseconds, one pulse like that. Okay, so now you start to do the math, you're like, wait a minute, that can't be right? You know, I can take my brain scan in 5 to 10 minutes today, and if I do the numbers, this will be a half an hour and 45 minutes. Yes, this was the principle like 30, 40 years ago. That's how they do it. There are new innovations that allow you to shorten the time. And the time it takes between the first echo to the time between the RF excitations, because each excitation you measure a voxel value, that's called the repetition time, TR. So there are a few important parameters: MRI acquisition, TE, TR. This must be reported in any of your publications. Okay, this is slow. How do we make it fast? We force the decay to happen faster, artificially. And that was what you saw in this direction here. I apply a pulse somewhere to do this flipping, and then I force the decay to actually happen faster. Okay. Two things. First, I'm doing the flipping. Second, this is happening naturally, but I can also introduce a pulse sequence to force it to dephase quickly. Okay. And these are known as a gradient echo technique. So the T2 decay used to be this way, but because I use a gradient to actually destroy the synchrony, I can force the signal to echo much quicker. But of course, it is at a weaker amplitude. And this is the principle of our modern imaging sequences, especially for MRI and diffusion imaging. Okay, I think I'm just going to go very quickly on these example pulse sequences, just to let you know what are the common pulse sequences used for anatomy and diffusion weighted and all that. Okay. For anatomical images, the common sequences, so these are the T1 weighted 3D images. The common sequences you see nowadays are the FSPGR, the fast spot gradient echo, and MP-rich, magnetization prepared rapid gradient echo. There's a lot of physics that goes behind this, but the reason I mention this name is because if you get either one of these, typically it's fine. Some people will argue a little bit about it's a bit noisier here and there, but our oscillation tools, open source, typically can handle both of them, no problem. I think it's actually more important for you to set up your voxel resolutions and make sure that you have sufficient contrast and things like that, rather than worry about which sequence. Okay, so back to the fast imaging. Remember, the way we're actually speeding it up is we are artificially forcing the spins, the direction of the magnetic field, to decay quickly and then rephase it. And that's using a gradient echo, that's what it calls. So instead of having, like we say, this whole bunch you have to repeat so many times per voxel, what you do is you only do it once, and then you just keep forcing the echoes to keep happening. And then as you do that, you start selecting different parts of the brain. And this method of imaging is called the echo-planar imaging, or EPI. And this is the one that gives you, full brain images, 4-dimension in like 10 minutes, 5 minutes. This is the innovation. Okay, but there's a problem, right? Because actually there are many problems, and that's what we're going through in this lecture. For one, the reason you're having it very fast, there are some advantages. One is it tends to minimize head motion, right? Because if you're actually imaging everything within 5 minutes versus imaging in 20 minutes, guess what? Your 5-minute image most likely will have less motion, right? Head motion. And you know why is head motion a problem? Because let's say you apply your pulse and you excite your magnetic fields, and then you move, and then this decays. Your coils are going to think the signal decay is coming from a different location. That's the problem with motion artifacts. So having a really fast imaging sequence under 5 minutes, people can keep their head still for about 5 to 10 minutes. You can actually overcome this problem. Second, you know all these T1 and T2 decays. Well, guess what? If you do the imaging really quickly, you actually don't have to, you actually can get images with a fairly consistent amplitude. But the problem is, as you try to get more and more voxels, you squeeze more and more voxels, you're starting to go on the tail end where it's having a decay. So these fast sequences tend to have a bit of a non-uniform maximum amplitude throughout the images. Okay. Right, can we go on? Now, I'll tell you the origin of the bold fMRI signal. Okay. So the bold fMRI signal, the T2 contrast, where does it come from? Okay. Everybody knows that oxygen is needed to deliver energy to our cells. And blood vessels carry oxygen, right? It goes through your lungs, you exchange the carbon dioxide and the oxygens get bound, and then when it passes through your cells, the oxygens gets released. This is high school biology. When neurons activate, when they fire, they need energy. And so they will, and when they activate, the hypothesis is, and I call it a hypothesis because I think people can prove it, but there are always exceptions in biology. The thought, the hypothesis is that when the neuron wants to activate, there is a demand for oxygen. So it's going to request more oxygen. And hey, guess what? The blood has a chemical known as hemoglobin, which has an ion in it, which is magnetizable. And what's great is when the hemoglobin is oxygenated, it is diamagnetic, which means it is magnetized. And when your blood cells, the hemoglobin in your blood cells, lose that oxygen, they lose their magnetizability. So now you notice that you have a state where your blood, if it's oxygenated, it has a magnetic field, which means it will probably come up as a strong contrast in MR. And when you lose the oxygen, the magnetic field goes away. So this is the principle for how we are detecting the Bose signal, and it's actually kind of an inverse reasoning. When there's more oxygen in your blood, in the local region in your blood, the blood actually has an increase, contributes an increased local magnetic field, which causes a faster T2 decay. Okay. So regions with a really fast T2 decay have increased oxygenation values, higher activity. And those with less less oxygen has less T2 decay. But the story is not that simple because the time course of how the oxygen goes up and goes down follows a particular function. There's actually an undershoot. That means the oxygen actually decreases first, because you can think there's a demand, so the oxygen all goes out, so there's a decrease. And then it takes about 6 seconds for the oxygen value to go up and peak. And then there's an overshoot. Typically there's more oxygen that's needed, and then it drops, and then it goes undershoots, and then it goes back. This is called the hemodynamic response function. And if you are processing MRI on an event basis, meaning that you're saying that something happens, I want to see what is the blood flow response, you need to take into account that the blood flow change has this kind of a delay. Okay? Right, this is just for knowledge. Right? This is all part of the pre-processing step. So this is the origin of the T2 contrast in bowl fMRI. The oxygenation or lack of oxygenation creates a local magnetic field or lack of a local magnetic field, which interferes with the T2 decay of the hydrogen spins. So typically, in fMRI, we have a sequence of three-dimensional images. Each of that three-dimensional matrices has an intensity value, which is the T2 decay. And that intensity value, and we are sampling usually about 2 to 3 seconds between each 3D image. And collectively that forms your 4D fMRI signal. Okay, why 2 to 3 seconds? Why 2 to 3 seconds between each of these spacing? Well, one is it's a constraint set by your epi. How many voxels can you squeeze into that short 2 to 3 seconds and still get good signal? And the second reason is it probably doesn't make much sense for you to sample beyond or less than 2 to 3 seconds because things change on the order of 6 seconds. The blood flow moves on the order of 6 seconds. So there's not much point from a physiological perspective to do finer sampling. The engineers will know, will smell Nyquist sampling theorem here, where you should just sample twice as fast as the maximum rate of change that you expect. Yeah. So that's kind of the hand-wavy reason behind that. In fMRI, there are two general ways you can take fMRI, or rather two general forms. One is you take the functional changes while you are performing a task. Let's say you are doing a cognitive exercise, you're trying to recall some parameters, and you are actively imaging at that time. The second is called the resting state functional magnetic resonance fMRI, and that's when you just think about nothing and you just let your brain go free. And amazingly, this is has been one of the key drivers of our network analysis of behavior in the brain, because in the last, I would say, the last 5 to 6 years, we have found so many interesting findings just from the resting state activity, which we'll have a chance to go through hopefully this afternoon, if not next week. So, and if you're doing a resting state fMRI, some people recommend between 5 to 10 minutes is sufficient with 2 seconds to 3 seconds sampling rate. If you want to do more, that would be interesting, and there are some reasons why you want to do more. Describe to you where does the origin of diffusion weighted imaging and how do we actually generate the nerve fiber tracks from this. Okay, this is also a T2 contrast mechanism, but it is used differently. Okay, the way it works is something like this. The diffusion weighted imaging, what it does is, let's assume that I have a static brain region. Nothing's moving in this brain region. I can artificially dephase this, and then it will rephase, and then I get some magnitude. Okay. Now let's assume that there's some flow, something that's flowing, moving in this. Okay. So I'm going to artificially dephase this, but when I start to rephase this, the spins that were defaced have moved to a different position, and something else has come in its place. And when I rephase it, I'm not actually going to get the same value as if it was static. Do you understand that principle? I'm doing something to some local population of H molecules, and if they don't move, if I do something to it, destroy the coherence, and I regenerate the coherence, I'll get the same value, more or less. But if I destroy the coherence and it moves somewhere else, and I try to re-establish the coherence of that same location, but the hydrogen atoms that have been destroyed were somewhere else, I'm not going to get the same value back. And that is the principle of diffusion weighted imaging. Diffusion weighted imaging tries to destroy the coherence locally, that is basically using the gradient dephasing to dephase to reduce the length of the perpendicular magnitude. And then if there's motion, the value will change. If there's no motion, you get a different value. And that's how you get contrast. Okay? And this actually comes from something called the statistical standard equation. This is the intensity value. Okay? This is the intensity value when there is no excitation to do this destruction and reconstruction. Okay? If I start destroying and reconstructing them, I have this parameter called B. And this B value is kind of a magnetic field in a particular direction. Because diffusion, okay, I'm looking at the direction of flow of water molecules. Okay, how does that relate to neurons? Well, if I have a neuron going this way, the water is going to flow from the cell body all along the axon. The water is probably not going to flow perpendicular to the axon. It just doesn't happen. That's not how the way neurons work. But if it does flow in the other direction, it means the neuron has been damaged. So this is something called an anisotropic diffusion. I will have a stronger diffusion in one particular direction, and that tends to be in the direction of a neuron's nerve fibers, or the myelin tracts, or I think there was a third one which I forgot the contrast mechanism. Okay, and there's less movement of water in the directions not in that line. Okay, so that's the origin of this signal. And I think I've got this sequence. Okay, and the most basic model you can get is you assume that the water is kind of diffusing at the same rate in 3 dimensions all around. It's called the scalar diffusion, and this is something called your average diffusion coefficient, the ADC. You get one value. And if you do diffusion tensor imaging, you are typically having a slightly complicated model where you're saying that I'm measuring the movement of water in 3 different axes, X, Y, Z, and if I combine them, I can get more or less the general direction of movement of water. Okay, so for this 3-dimensional model, saying I want to measure the movement of water by measuring the movement of water in X, Y, and Z, you need 6 images plus a 7th, which is the image when you actually don't apply a B field in any direction. Okay, so this is the basic diffusion tensor imaging sequence, and you can think about it as the model like this. If the water molecule was moving everywhere, this is an isotropic diffusion. This is kind of the matrix that you will get. And what I'm trying to show with all these equations is basically this idea here. You use your pulse sequence to generate this B parameter here. And this B parameter is the number of directions you kind of are measuring the direction of diffusion. This D parameter here, that's what you're measuring. That is the diffusion, the rate of diffusion. That is your measurement, your intensity value in the image. And there, you can make this model very simple. D can be just a single number for one voxel. Okay, each voxel has a single number of D. Or D can be a combination of 3 numbers, diffusion in X, and Y, and Z direction, for each voxel. Or as we'll see for tractography, D is a high-dimensional vector giving all the directions. Each voxel has multiple D values. Okay, so it's that same framework. It's just how detailed a model you wish to use to capture the direction of diffusion. And remember, the direction of diffusion is the direction along which we presume is the nerve fiber tracts, the myelin tracts. So if you use a diffusion tensor model, you're looking at the diffusion along 3 directions. So in this case, if the diffusion is isotropic, if the diffusion is sort of the same rate at X, Y, and Z, your D value will be a matrix with just 3 values. But if there is one particular direction that is very strong, which indicates that there's probably a nerve fiber there, then you will get a full matrix here, 9 values. And the reason you need 6 images is because there are 6 unique numbers. The matrix is mirror fit. Okay. So, key point, I'm just explaining the concept of diffusion imaging. Basically, you are looking at measuring how water moves, what is the rate of water movement around a voxel. Okay, and you do that by disrupting the magnetic field and then trying to rephase it. And then if there's movement, there's going to be a change. If there's no movement, you get something that is static. Okay, and then you can start with the simplest model where you're just taking one number for an average diffusion. You can go to a more complex model, which you're saying that I'm just going to measure the diffusion in X, Y, and Z directions. And this is where you get something called your DTI scalar maps. These are some equations showing how this is obtained. Okay. And you have your fractional anisotropy, your mean diffusivity, your radial diffusivity. They're all parameters like that. But we're not going to be focusing in this course on DTI because DTI is a little bit old school. It's useful for you to know, and it's useful for you to know because with the main direction from each of the voxels, you can start to stitch together a direction, a line like this, and this approximates your neural fibers in the brain. You can generate a 3-dimensional image like this. Okay. And what is the subject matter of this course is how do you go from this wiring diagram with all the location of the individual brain regions here to create a connection diagram of the brain, a circuit diagram of the brain, and hopefully after tomorrow you will have the mathematical tools to analyze the properties of this circuit diagram. So this circuit diagram is called a structural connectome. Okay? So now you can see how we've moved coarsely from a diffusion weighted sequence to getting some of these parameters to actually forming the tracks. And all these are done by computer algorithms. They're open source tools. You probably don't even need to go into the mathematics to understand it, but to use it effectively, you need to understand the concepts so you can choose. Because today, with all the open source tools, your problem is more a problem of the right choice, the informed choice, as opposed to the right algorithm of number crunching. Okay, this is nice and great, it's a good pedagogical tool, but there's a problem. Diffusion tensor gives you one principal direction, X, Y, and Z. It doesn't work well in locations where you have multiple directions of where the fiber crosses. So this is an example from a publication from Whedon, who was the inventor of the diffusion spectral imaging. So with DSI, you actually can resolve these fine fibers. With DTI, you see all the fibers just go in one major direction. So hey, our 3-direction, 6-value model is kind of falling short because we don't actually get an accurate representation of the nerve fibers. And this is a problem. So what do? Well, remember I told you the Sketch-Giles tensor equation? This one here, this is the source of all we're doing. The B is where you play around with your pulse sequence parameter to sample all the directions of motion. The D is basically your model, your value that you want. And we had a very simple model, just one value, and then a more complex one, the DTI model in 3 directions. To resolve multiple fibers, you actually have to go to a model-free approach, meaning don't just measure in 3 main directions, measure in all directions. And that's the principle. So diffusion spectrum imaging, or what they call it, the more general term is skew space imaging, is you're finding the gradients of the diffusion in all directions. And the different techniques that appear here are just different in the way they represent the distribution of diffusion in directions. So you can imagine the simplest model we had just now, the DTI, was the diffusion only in 3 perpendicular axes. in Q-space imaging, we are talking about the diffusion in all dimensions. How do we represent that? So you can actually represent that as a probability function over a sphere, right? Because a sphere gives you in every direction, and each point of the sphere indicates a direction. There is a probability number associated with that, probability of diffusion going that way. So that is what you call the diffusion orientation distribution function. So if you visualize it, it looks something like this, something funny like this, right? So you can actually see that this is actually a rich descriptor, because locally here you actually see that there are diffusions in this direction, this direction. Here you see the diffusions tends to be just more of horizontal. Typically the diffusion spectrum imaging protocols, they are sampling, they are measuring in all directions. They are not giving any kind of model, not in 3 dimensions or that, right? And the reconstruction algorithms that you will use, they vary, they are different only in how they represent these distribution function and how they obtain the distribution function, the distribution values. Okay, so it's still not quite clear which is the best approach, but I think you should all go for diffusion spectrum imaging from now on. Okay, so this is an example of how you are sampling. So if you compare one of these balls to DTI is just 1 point, 1 point, 1 point, 1 point, 1 point, 1 point in 3 dimensions, 2 points each dimension. If you're using a distribution spectrum scheme, you are talking about sampling all in that direction. And just a matter of detail, one scheme actually does the sampling on the square grid, another scheme actually samples it on a sphere. Okay. So the sphere technique is called HARDI, high angular resolution diffusion imaging. Typically you go for 64 brain images with a p-value of 3000, only one p-value. Diffusion spectrum imaging, you have a table of p-values and p-vectors. Okay, so what do I mean by p-values and p-vectors? I told you we are measuring the diffusion along specific direction. How do you measure that direction? You apply your magnetic field, your p-value, in a particular direction. So the p-value is the strength of that magnetic field in that direction, and the p-vector gives you the direction in which you are sampling. Okay. So with a DTI, you expect a 6 p-value, 6 p-vector table, right? But typically DTI is now done with about 33. So I think 32 directions and 1 p-naught. You still need a p-naught, which is your brain in default without any magnetic field indicating the direction of diffusion. Okay. Yes?
So in diffusion spectrum imaging, you said it's done in all the directions.
Yes, okay, I'm glossing over because they try to split it up, they actually try to take it on 1 quartile and all that, but the key point is you actually need to measure densely over all directions. And then there is a practical trade-off between how many directions can you measure before people start to move and they don't want to be in the scanner versus accuracy. And so the numbers that people actually get to be quite okay, I think there was a recommendation for about 101 directions for DSI. And DSI Studio, if you actually go to the website, they actually have the p-vectors and p-value tables that you can use. The first DSI that they tried, I think it was about 45 minutes, was about 515 directions. And there was a proposal for HARDI, which is 1 p-value, because the diffusion spectrum imaging will have multiple p-values, because it's trying to sample. HARDI, they were able to argue out a case where you can actually measure on the sphere with just 1 p-value and there's 64 directions. But there are some papers that actually say you should still stick to something called a multi-shell technique. Multi-shell means you use multiple p-values. Okay, why? Because this is just the key observation. When your p-value is high, means you're further along the shell, your shell becomes bigger. You actually have greater sensitivity, accuracy in the orientation direction. So imagine if your sphere is really small. So the B is actually like the radius of your sphere. The B is really small. 2 points at like 20 degrees are very close together. But if the B is very high, the sphere, 2 points are actually far. So you actually have better angular resolvability at the high B values. But unfortunately, the signal to noise ratio, the accuracy of your signal is higher at the low B values. For various reasons. We're not talking about SNR, but this is a problem in MR imaging that how much of it is the real signal that you're measuring and how much of it is the underlying noise from everything else and someone's cell phone in the MRI room. Right? Yeah. So this is a trade-off, and so people, I think it sort of makes sense that you should go for a multi-shell technique because of this reason. DSI would be a natural alternative, but you also should know that hardly people have used it and I think it's okay. So take-home point from this, you now understand qualitatively how are the diffusion tracks obtained, why it's quite important for you to pick a good diffusion-weighted imaging scheme because of accuracy reasons of the connectome. And I've given you two kind of parameter sets that can get you started. And you just need to know these parameters to do the reconstruction. So you just need to know the p-value and the vector table, you can do the reconstruction. But for the interpretation, you actually have to pay attention to this meaning and all these problems. The reason you have to go through this because I want to walk you through the main sources of error. What you measure is not what you get. So it's not YCV like that used to be like 20 years ago. We talk about computer software and processor. What you see is what you get. It's a big thing, right? So in this kind of MR imaging, it's not quite that. And you need to understand why. First, motion artifacts. You've now understood that you're actually acquiring the intensity value voxel by voxel. Right? Each echo is a voxel value. And you're playing around with the gradients and the B1 to actually target each voxel. And if you move, guess what? You get a blurring. So you can move anytime, right? You can move when you are setting the gradient to spatially localized and that messes everything up. You can move while you're actually reading out the value, so you get half of the value in this voxel, half the value in this voxel. So that's a big problem. And typical motion artifacts, you will appear as ghosting or blurring of values. And I think you can imagine why this is a problem, right? Like let's say diffusion values. So I'm actually taking the diffusion from here to here. And then I move, and then I'm moving like 4 voxels, right? So you'll be like having like spurious connections and things like that. Or in fMRI, you're moving, so this part was supposed to activate higher, and then you move, and then it looks like it's a broader region of activation, but it's a lower activation. So these are the problems. So motion is bad. I think the only way you can think about motion correction as having several layers, that is between 3D images, which is a little bit better. You can still correct it because you can look at the anatomical features and try to match that. But if they're happening within voxels or between voxels, then you're in trouble. So motion is very big enemy. The second one is a little bit interesting and difficult to understand, but it's okay. I think you can do it. Now, I told you that we were trying that the rate at which the signal, the frequency, the rate of change, right? It changes depending on the local B field value, the local magnetic field value in the brain. And then we use that principle by applying a field gradient, that is changing the magnetic field slightly over space to get spatial encoding, to actually get different locations. Now guess what? The magnetic field in your brain is not uniform. So the same water molecule in different parts of the brain is going to precess at a different frequency, because some parts have a bit more blood, some parts have less blood, some parts have ventricles and holes, and that's going to actually change the local magnetic field. And that is known as the magnetic susceptibility variation, or sometimes you call it susceptibility variations. So that's the problem. I'm telling you that's the problem. Everyone's head is different. And everyone's head probably at different times of the day, depending on what you eat and all that, probably it's going to look different. We just don't quite know, but we know it's different. Okay. The first order of business, people apply something called shimming. There are higher, like fancy magnetic fields that in the MRI machine that try to correct for that. But that's not always possible to do perfectly. And here's where the signal processing comes in. So with this field distortion, you can imagine that at certain locations, it actually spins faster, or it oscillates faster, oscillates slower. And since we're encoding position with frequency, we are detecting that signal from that point. It will appear as if that signal is coming from a different location. Do you understand that connection? That we were saying that the signal actually has an oscillatory portion, that's the frequency, and the decay, we're measuring the decay, but the oscillation is useful. we try to make the oscillations at different locations in the brain slightly different by making the magnetic field slightly different across the brain, by introducing a magnetic field gradient. But the head has a non-uniformity itself, which is going to really also change or slightly detune the frequencies. So if I have, if I'm measuring, I say, frequency A is coming from this portion, but because of the susceptibility, there's a bit of different magnetic field, it looks as if the signal from here is not actually going to occur at frequency A, it's going to occur at frequency B. So I'm measuring from here, but because of the local susceptibility, it appears like the signal is going to be coming from here. That gives rise to geometric distortion, shape distortions. So you actually see kind of like horns and all that on the MRI, or worse, what's really worse and insidious is this tends to happen at the boundaries of the ventricles, so and between the parietal, temporal, and the frontal lobes on the inner sides. So it doesn't affect the brain equally. That's problem number one. Number two, it affects at certain regions. Number two, it will change the shape sometimes. So this is a problem to look out for, right? And so the way we do this is we get a map of the field differences. We can actually measure the differences in local magnetic field difference across the brain. And then we try to undo this computationally. Because if you know at this point the magnetic field is a little bit higher, so you will be, and you know by how much, you can actually say, okay, if I'm actually measuring at this point, I actually need to reduce the frequency by a certain amount. Okay, so you can actually do the correct mapping. And the way to do this really is, okay, let's go on. Okay, so this is an example of that. This is an example of a T2 with this distortion. So it actually doesn't look like this, and these are all changed. And I think the clinicians among you will see that the cortices, the sulci are not properly well defined. This is a phase map. This is actually the difference between two closely recorded echoes. I mean, I may talk about these echoes and corrections later, like the actual scheme and how is the correction done in software. But for now, just understand that we need a phase map. This shows the severity of that shifts, and it is a three-dimensional image. Okay. And the gradients, and this distortion actually is worse in the deep brain, subcortical, frontal, and temporal lobes. Okay, now this is where the epi part comes in. So remember that I was telling you about these fast sequences. This was the secret to getting really fast imaging. I tilt it and then I destroy and recohere, dephase and rephase with the gradient echoes really quickly. So I'm actually acquiring signals very quickly here. But because I'm acquiring signals very quickly here, the electronics here are being put under a lot of stress. So they are in a mode called a low bandwidth mode. Okay, so they don't get so much detail on the oscillation. So there might be some errors that happen there. And when this, yeah, and when you're doing this really fast, okay, the gradients that you actually put out are not exactly what they should be. And the gradients that you really impose onto the brain may remain for a short time at that region. So what I'm trying to say is these are all different ways that this fast sequence will really mess up the local magnetic field value. And that is why for epi sequences, which are the diffusion weighted and the fMRI sequences, geometric distortion is a big problem. Problem number one, the local brain field distortions. Problem number two, we are not actually recording the actual signal from each voxel with a high accuracy because we had to do it so fast, we can only take a few measurements at one time. So this is called a low bandwidth problem. Problem number three, you're actually exciting the magnetic fields and then trying to destroy it and then you go into a different one. So there may be some residuals there which change the local magnetic field. Problem number four, the magnetic field that you're applying may not even be at the exact value because they need to change so fast. All this lead to a grand mass that you actually have some kind of residual, non-uniform, local magnetic fields in the brain, which cannot be corrected by the MRI scanner because they are happening live, they are a dynamic process. Okay, so the local MRI scanner can correct for the magnetic field inhomogeneities in your natural brain, but these inhomogeneities are actually arising from the pulse sequence. And so the way we solve it is we take two images, change the direction of the slow phase encoding. So here is an example in one direction, in another direction. So you can actually see there's a greater distortion here, and then when you flip, there's a distortion here. So it's the same brain, but taken in two different directions. One from the front of the back to the front. Right? And then there's some open source software that can undo these changes. But key take-home point, first, motion is bad, watch out for it. Second, make sure you are making all your corrections for magnetic susceptibility, and I just told you what are the different sources. And oh yeah, magnetic susceptibility can also cause differences, small changes in intensity values, like maximum intensity values. So this looks like your brain is going through some kind of low pass filter. Certain regions are brighter, certain regions are darker. And this is called dropout. And the third source of error actually is it's actually arising from the rapid switching of your gradient currents. Remember, I told you the gradient coil is what is imposing that space mapping on your brain by slightly changing the field and slightly changing the frequency. Well, when you do that very fast, the coil itself in the switching will have some electrical imperfections. There will be some additional currents that just get generated there. I guess the additional currents generate additional magnetic fields which interfere with your signal. Right? And this again gives rise to geometric distortions and ghosting, that is overlap of intensity values. So all these, there are software techniques. The three major classes are motion, magnetic susceptibility, and eddy currents. There are some tools already out there, open source, that can help you correct for that. They're not perfect, but they do a pretty decent job. I'll tell you a little bit about a standard processing workflow. And of course, in neuroimaging, nothing is really standard, but this seems to be from a good group, and it's got some of the major corrections in there. So it's something good to think about. Okay? So we've discussed this morning about a raw fMRI bowl signal. It's a four-dimensional matrix. You get a 3D matrix of numbers, and you have a bunch of these 3D matrices. Each 3D matrix is obtained in one with some time resolution in between. Could be 2 seconds, could be 3 seconds. We'll talk about the hemodynamic response function. But now you end up acquiring this fMRI bowl signal, and you know that if there's motion artifacts, there's magnetic susceptibility, there might be geometric distortions, there might be a little bit of ghosting and bleed through and all that. So now you have this signal, and what do? And what are the problems? So in pre-processing, and this is the reason why it's called pre-processing, because you're trying to clean up as much as possible the raw data set and to undo some of these errors. Typically, your raw bowl fMRI, your four-dimensional matrix, must be corrected, must be cleaned up before you actually can generate the functional connectome. Today, I'll be talking about two clusters of correction and point you to a tool that will be able to do this correction for you automatically. And if the stars align and I can get the server running, by next week, you would be able to have some hands-on and actually run this tool for yourself. Okay. The first set of corrections deal with trying to undo distortions in the data, and the second set of processing steps is not for corrections, but is to prepare the fMRI data set for useful interpretation. You just want to match it to known brain locations, known brain areas. Okay, so I'm introducing a new term now, and the term is workflow. Some people call it pipeline. They kind of mean the same thing. So this is one example of a workflow. Now, what's a workflow? Workflow is just typically a sequence of processing steps. There are many things to do, and there are lots of open source tools available. And fortunately or unfortunately, it's more unfortunate than fortunate, tool A may have a good module to do something, and tool B will have a better module for doing something else. And what you really want is the flexibility to use the best modules from each open source tool together in an automated workflow. Okay? So hopefully we'll be able to get to that next week, the tool to be able to help you assemble that. But today I'll just talk about, I'll focus you more on the sequence of steps. First, the understanding that there is a sequence of cleanup steps, and these can be pretty complicated, but the key take-home point is you understand why they're necessary, what do they do, and make sure that in some future processing, you actually make some allocation for that. So fMRI prep is a workflow from the Podrak lab at Stanford. There is an open source tool for that. I hope again next week we'll be able to run this once the servers are up. And this tool actually does three major types of correction on the fMRI data. Okay, the first one is called slice time correction. Now, you had this exposure just now of the echoplanar imaging, where you saw how you were acquiring the intensity values of the brain at every single voxel, and you actually just go one round the axial plane and then down the next axial plane and third axial plane and the fourth axial plane. And between one 3D brain to another 3D brain, there's about 2 to 3 seconds. And this tells you that each intensity value, each T2 contrast value of each voxel is not acquired at the same time. That's an important point, especially if you have a big time spacing between two subsequent brains. Because statistically, you are processing this assuming that all the voxels change at the same time, but they don't. And that has some possibility to mess things up, right? Because if this is your first voxel and this is your last voxel, this is going to look much closer to the activity in the next time domain, the next time epoch, right? So slice time correction tries to fix this. And the way it does it is, again, that same idea of interpolation. I know what is my value at this time point. I know what is my value at the next time point. I can create a function, it could be a spline function or something like that, that tries to match the trend, and then I take my best guess of what the intermediate value is. Right? Except that that was how I described the resampling problem, that you actually wanted more intensity values in between space. Now what we're trying to do is we are trying to shift the value that you read in time. The second thing that is done is the head motion correction. Because you are taking 10 minutes, 15 minutes, 5 minutes of fMRI, and the person might have shifted the head a little bit. And the way this is done usually is looking at the general 3D shape of the brain, or sometimes trying to match features. Between each 3D brain at each different time points, you try to get an affine transform that maps them, kind of aligns them together. Okay. So this is a correction that can be done with, that is done when you do the head and motion correction. And there's something that actually complicates it a little bit. Typically the head motion correction plus the slice time correction is done at the same time simultaneously. So to correct for head motions throughout the fMRI acquisition, you do a rigid body affine registration, linear transformation. Rigid body is a linear transformation. And this tends to be done with slice time correction. Okay. Now here you see at the lower left here, I have actually the name of the open source tool, as well as the specific function in the tool that the fMRI prep workflow is using. So for slice time correction, the AFNI toolbox uses the 3D T-shift. It's good for that. So then the question is, probably people found that the FSL MC Flirt toolbox was much better at head and motion correction, so they prefer to use this one rather than any other toolbox. So you're starting to see that in order to assemble all these pieces of corrections, we're actually using open source tools from different open source programs and libraries. That can become a royal mess. But this is why a workflow is nice, because it provides a way, it has already provided a way that has integrated how to call these tools together, so that you just type one command, you launch it, it will perform all these functions using the different open source toolbox for you. Okay, so back to the third step in the correction, the susceptibility distortion correction. So here we are trying to undo the effects of a non-uniform local magnetic fields due in the brain of the subject themselves. And here there are just two ways to actually obtain this map. You actually have to take an extra step to obtain the MRI with a certain protocol. The first, you have a choice. The gradient echo acquisition, you can just have two closely spaced gradient echoes of one axial plane. So you're taking one axial image, you configure it, it's called a double gradient echo sequence. It's going to get two versions of the same image, except that those two voxels are acquired very rapidly, one after another. It's making this same measurement at the same voxel, but it's doing it twice. And the timing between the two voxels is what's going to help the open source tools undo these errors. So here the key point here is, if you're going for this, talk to your radiographer, ask them for a double echo gradient echo acquisition. That will give you two magnitude images. So these are magnitude images, they are intensity images, and one phase difference image. And with these three images, you should be able to undo the effect of the susceptibility differences, distortions in the brain. The second approach is to actually acquire an entire 3D stack of the brain. Just one fMRI, but you do it in one direction. The first direction is the phase encoding can go from the anterior to the posterior direction. And then you acquire that very same 3D stack of the brain, but this time just flip the direction of encoding. You start acquiring from the, just now I said posterior to anterior first, then the second one has to acquire from anterior to the posterior direction. So again, this is something that you ask your radiographer for. They're going to produce two whole 3D image stacks, but the difference in these image stacks is whether you're acquiring the voxels from the back to the front first, or the voxels from the front to the back first. So you need both. And with this information, you should be able to back out the susceptibility distortion correction. When I say should, it means as an open source software, it's part of this. Okay, so I can move on. Okay, so the first step, the first set of corrections are more of just making the data more realistic and more suitable for our analysis. The second set actually is preparing it for, preparing to give it some context, I would say. And typically here you're trying to register the location of the brains to some anatomical context. Okay, usually the fMRI neuroimages tend to be acquired at much lower spatial resolution than your anatomical images. Your anatomical images you might acquire at 1 millimeter or 1 millimeter like isotropic, or even half a millimeter. Whereas the fMRI, things that are common because of the speed requirement, you need to acquire a lot. It's about 3 millimeter isotropic. So you have a poorer resolution, meaning that you can't quite say with as much precision, as much localization precision, how much the blood flow has changed. Okay? And in order to help us to understand which parts of the brain are changing, usually we try to compare the fMRI stack to a real anatomical stack. This is where the registration comes in. Because once it's registered, you can pretty much do an apples to apples comparison. Because you know that if I've got, if I've got two brains, I've got a coordinate here, or a location here. I've got a location here. I can actually use the affine transform, it's a two-dimensional matrix, and we need to actually label the parcels. This is where you start to see the importance of actually being able to extract the parcels from a brain in order to correlate, to assign the activity of the brain pattern to that particular parcel. And so that's actually the second part of the fMRI pre-processing, where you are also giving it an anatomical image, a T1 image. Okay, what's going to happen is the software, the workflow is going to actually remove the skull. Okay. Then it's going to identify three main brain regions: the white matter, grey matter, cerebrospinal fluid. And based on the boundaries of these three different cell types, cell types in a way. CSF is actually not, it's just a space with fluid. You're going to perform a registration of the structural brain to the functional brain so that you can kind of align them together. And then you can actually apply other open source tools to create structural parcels or functional parcels to tell you which group of voxels should be grouped together meaningfully, and from those groupings you can then map that to the fMRI time series, and then you can calculate the connections from that, the connectivity, the connectivity strength from that. So that's the importance of this bit. This one is just kind of again, there are two ways of doing the brain comparisons. One, you're comparing with a group. So you probably need a reference brain, and that would be the MNI atlas. So you need to actually register the structural brain to the MNI template, the fMRI brain to the MNI template, and then you can bring everybody into the same space to compare. Second, you're actually talking about maybe an individual or just conceptually on the parcel. So you actually just do the parcellation on that particular individual's brain, and then you will register the fMRI brain to the structural T1 with the brain. Right, I'm almost